Hello, this is Miss Moore, and today during chemistry, we're going to continue our discussion on single replacement reactions. Today, we're going to focus on single replacement reactions using nonmetals. And today's essential question, how are the products of single replacement reactions determined? We are going to start with a quick review of diatomic elements. Remember that diatomic elements are atoms that can never be alone. So an example that you've seen before is oxygen. Oxygen is one of the diatomic elements. When we have oxygen in this formula for water, the oxygen is not alone. He is bonded with other atoms, so he's okay. However, if I just write in oxygen, that's where the problem comes in. That's when this whole diatomic thing comes in. So you can never write just a single oxygen with it not connected to anything. You'd put a 2 there, and that fixes the problem. So diatomic elements are either bonded with another atom, like in H2O, or they're bonded with themselves, like with O2. All right, so the diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And I gave you guys 2 different ways to remember those. The first is remembering the word Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. That's the most common way to remember it. I use HN7. The diatomic, looking at the periodic table, starts with H, then goes to N, and in a line shaped like a 7, the rest of them. So let me show you on a periodic table what that would look like. So we start with hydrogen, then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, HN7. Doesn't matter which way you use to remember, but definitely try to remember these. Not try to, you need to remember these. And now, on to the star of the show, single replacement reactions. So single replacement reactions, also known as single displacement reactions. During a single replacement reaction, atoms of one element replace the atoms of a second element in a compound. And I have written below in blue the general equation for a single replacement reaction. In this case, we have a single atom, single type of atom. And for today, our Y, or our single atom, is going to be a nonmetal. And then we have an ionic compound. Okay, and when we're talking about single replacement reactions with nonmetals, the ones that are going to be switching places are the 2 nonmetals. So Y is going to switch places with A. And as a reminder, single replacement reactions need to occur with ionic compounds. All right, let's go on to the steps to write or complete a single replacement or displacement reaction. And as we're going through the steps, we're going to work through the example I2 plus HF. All right, so first step is to determine which atoms are cations and which are anions, or would be. All right, so we have I, H, and F. So we'll start with I. I, you can see right there, is a nonmetal. So to become like a noble gas, he needs to gain 1 electron, becoming isoelectric with xenon, making him a I with a 1 minus charge. So I 1 minus. All right, H is next. H right here acts like a metal. He's hanging out with the metals, and metals lose electrons. And he only has one electron, so he's going to lose that one, making him an H1 plus. And then we have F, fluorine. Another nonmetal. Nonmetals again gain electrons. Fluorine will gain one electron, becoming isoelectric with neon and giving him a 1 minus charge. Okay, so I can say this, the iodine and the fluorine are our anions, and the hydrogen is our cation. All right, so step 2, determine which atom is going to be replaced. And a negative or a nonmetal is, so these two here are your single atom, are going to replace a negative or nonmetal in your ionic compound. Okay. So looking at this, it looks like we're going to have, I'm trying to think of how to write this, that we're going to have iodine swapping places with fluorine. Step 3, write the skeleton equation. So let me put our example back. We have I2 plus HF produces, and we had, this was a 1 minus, 1 plus, 1 minus. All right, so when we write the skeleton equation, we've determined that iodine and fluorine are going to swap places. So fluorine's going to be by himself, and we're going to have hydrogen, which has a 1 plus, hooked up with fluorine, which is a 1 minus. I know this isn't correct yet. Don't worry. That's the skeleton equation. All right. So next, make sure that all ionic compounds are neutral, and there's another step that goes with this. And really important, check for diatomics. You need to do both these steps for the products every single time. Oh, I guess I didn't point this out. And is anybody yelling that I wrote this wrong? I hope you are. Not supposed to be HF, is it? It's supposed to be HI. Okay. Hopefully you note that I did not take the 2 over. You never take subscripts with you. Don't take the numbers with you. Just the letters, just the atoms or ions. All right, so now let's make sure that the ionic compounds are neutral. Well, we have H1 plus and 1 minus. We have the same number of positive and negative charges. So that's neutral, so we're good there. Our formula is going to be HI. We also need to check for diatomics with the single atoms. And F is indeed a diatomic. So, and he's all by himself there. So we need to add a 2. The last step is to balance the equation. Let me rewrite this down here so we have a little bit more room. I2 plus HF produces F2 plus HI. All right, we have I, H, and F. Let's see, 2, 1, 2, 2, 1, 1. All right, so to make this guy neutral, let's add a 2, giving us 2 hydrogens and 2 iodines. So we fixed our iodines, messed up the hydrogens. Put a 2 here. We have 2 hydrogens. And I don't know how to count, do I? Because this was supposed to be a 1 earlier. Sorry. 2 fluorines. And we're neutral. All right? So now let's try one more. And you know what? I don't want to try that. So don't write that one down. I want to change this up a little bit. Let's get rid of this guy. Give me a sec. I don't want to do this one. I want to do Oh, sorry, getting there. All right, I want to do Mg plus, no, I don't want to do that. All right, ignore that one. We are going to do Br2 plus Mgi2. Okay? All right, first step. Figure out the charges, who's the cation, who's the anion. So we have bromine, nonmetal. He's going to gain an electron, becoming a 1- charge. Magnesium is a metal. He's going to lose 2 electrons, giving him a 2+ charge. And iodine, non-metal, he is going to gain an electron, giving him a 1- charge. All right, so who is going to swap places? The 2 negatives, right? So bromine is going to swap with iodine. And remember, we do not take the subscripts with us. So iodine is now going to be by himself, and magnesium 2+ is going to hook up with bromine 1-. Okay, so now we need to check for diatomics and make sure our ionic compound is neutral. Iodine is indeed a diatomic, right? Hofbrinkel or HN7. So we need to add a 2 here. And magnesium and bromine, not a happy couple. We need 1 more bromine so that we have the same number of positive and negative charges, which means our formula is going to be MgBr2. All right? Okay, last step, balance. Br, Mg, I. Okay, I really wrote that messy. Let's try that again. Br, Mg, and I. We have 2, 1, 2, 2, 1, 2. We are balanced. Woohoo! All right, guys. Before I say goodbye, I want to remind you that I, so far today, have been implying that every time you have a non-metal, it will always replace a non-metal. That is not true, and I'm going to talk to you about how to figure out when the reaction would actually occur, when the switch would actually take place in a future lecture. All right, with that, that is it for today. So have a good one.